and the conference is on geometry, groups, and mathematical philosophy. It is an international conference in honor of Professor Ravi S. Kulkarni on his 80th birthday. So for this conference, I welcome all of you. And today we have the first session by Professor Nitin Nitsure. For this, I request Professor Dilip Patil from Indian Institute of Science, Bangalore, to chair the session. And before that, I request Professor Ravi Kulkarni to come here for 1 minute.
Oh, okay.
Yes, Professor Ravi Kulkarni is here. Yes.
Okay.
Okay, thank you.
Okay, hi Nitin.
Yes. So now I request Professor Dilip Patil from Indian Institute of Science, Bangalore, to come here and chair the session. Got it. All right. Good afternoon, everybody. It is indeed a privilege to chair this first session of this conference in the honor of Professor Ravi Kulkarni. I want to wish many more healthy and happy years much ahead to Professor Ravi Kulkarni. And let us start this first session. And the first talk is by Professor Nitin Nitsure. Most of us know him already very well. He will talk on curvature, torsion, and quadrilateral gaps. So, over to Nitin.
Thank you, Dilip. It's a great honor to talk in this conference in honor of Professor Ravi Kulkarni. And let me begin by a few words about him. I have had the good fortune of knowing him for nearly 20 years. And all the time I have been very impressed and I have learned a lot from his multi-dimensional intellect, as I might call it. So at the same time, he's a differential geometer, an expert on Lie groups, complex analysis, and interested in all parts of mathematics, including my subject algebraic geometry. Also, he is a big Sanskrit scholar, Indologist. He knows a lot about Indian history, philosophy, and so on. So always it's a great pleasure to meet and discuss things with him, anything under the sun. He is very curious about almost everything, thinks about almost everything, has deep insights to share. And but that is not all. If somebody was only such a deep thinker and scholar, you would say that's something fantastic. In addition to that, he is a very energetic organizer who has helped all kinds of institutions, journals, places like Bhaskaracharyya Pratishthan, NCM, the Ramanujan Mathematical Society, and many other things he has helped organize and run. But that is not all. A very rare thing is he is a very generous donor, and about this he himself does not talk much, and so I don't know exactly, but whatever little I have come to know about his donations, it's really very generous and truly extraordinary. So it has indeed been a rare privilege to meet a person like this. And so before I begin, I like to take this opportunity to wish him all the best, many, many more years of healthy, energetic, intellectual life. Okay, so now let me begin my talk. It is about curvature, torsion, and quadrilateral gaps. So let us talk about curvature. This is curvature. Let's begin with curvature of a surface. So one simple way that curvature manifests itself is by how triangles behave on a surface. So you know that on a Euclidean plane, if I have triangle, then alpha, beta, gamma add up to pi. However, if the surface is curved, the answer turns out to be different. A curved surface on, say, the earth, a triangle. So now straight lines are replaced by geodesics. So all these things are geodesics, the shortest paths on the curved surface. And if I take such a small geodesic triangle and add the thing, then it does not become equal to, but can be more or less, and alpha plus beta plus gamma minus pi equals integral of the curvature, so-called Gaussian curvature, on this area, on this triangular area. Okay, integrate the curvature on this and you get alpha plus beta plus gamma minus pi. If there's a constant here, I forget, might perhaps there's 1/2. You can easily test with some triangle and see. Okay. So there are many other manifestations of curvature. This is something which is intrinsic. So Gauss, though he defined Gaussian curvature in terms of the embedding of the surface in R3, he proved that it is something intrinsic. And here is the formula, which is known as Gauss-Bonnet formula, which tells you what's the curvature in an intrinsic manner. Now, a few years ago, in 2018 to be precise, I was asked a certain question by Professor Rajaram Nityananda, who is a famous physicist. So here is his question. So Nityananda's question says that I have some curved surface. So we are on some curved surface, angles and whatnot, all kinds of things are on it. And I start at a point, let's call it P0. And I go on a journey. I take a vector, starting vector. Let me denote that starting vector in red and call it U. And now I'm going to travel along this starting vector. I'll show my travel in black along a geodesic till I travel a distance S. And then I'll turn in 90 degrees and repeat my journey. Okay, so this is a right angle. And then I again turn in 90 degrees and repeat my journey and come to some point. So let's call this P0, P1, P2, P3. And then I again turn to the left in 90 degrees and finish my journey and arrive at a point P4. And now you can easily convince yourself that if the surface is curved, look at some example on the sphere if you want, you will not come back precisely at the point that you started. Unlike in the Euclidean flat plane where you will be back and this will be a square, all four angles 90 degrees, all four sides S. So this is S and this is also S and this is also 90 degrees and this is also 90 degrees. And this funny thing has opened up here. This, how much is this? How much is P4? And of course, it's a function of S minus P0. And now you may wonder, what do I mean by subtracting 2 points? For that, simplest answer is you take any embedding in any higher dimensional Euclidean space and take the difference there. Actually, you can take difference in the values of any function, and then it will tell you how much a function changes from here to there. Okay. So this Ps minus P4s minus P0, this is the quadrilateral gap. This is the quadrilateral gap of my title. curvature, torsion, and quadrilateral gaps. And his question was, how much is, the question is, how much is this gap? And I'm going to answer this question. And then I'm going to go on to multidimensional manifolds with affine connections. They may be Riemannian, and use such gaps or their multidimensional analog to recover the torsion and curvature of that connection. It might be a Riemannian connection, in which case there is no torsion, and then by such gaps, I can recover the Riemann curvature tensor. Okay. So let me answer this first question straight away. How much is this gap? But before that, let me take a variation of this question. So instead of going along a quadrilateral and finding this gap, I might as well take another journey. I might travel from here to a point which I'll call Q1. This is S and this is 90 degrees. And from here, I might again travel in 90 degrees along a geodesic distance S and come to a point Q2. And so another avatar of the gap will be Q2 of S, P2 of S minus Q2 of S. Okay, let's put it in this sign because then the answer comes better. So this P2 is also a function of S. Everything is a function of S. So this is Q2 of S, this is Q1 of S. And it turns out, and I won't tell you all the details in this lecture, I have already published the paper, that if you approach via this or via this, the answer turns out to be the same, but this is easier to handle for many obvious reasons. So now the answer is this gap P4S minus P0 is of the order of S cube. So it's really very tiny. So on the earth, if you travel for a kilometer, this will be like a meter or less, millimeter, whatever, cube of that. So the precise answer is this. So if I take P4S minus P0 and divide by S cube and take the limit, okay, this limit exists. This limit is a certain vector, and I'll tell you what that vector is, but first I'll tell you its magnitude. The magnitude of this is the Gaussian curvature at the point P0 divided by √2. This is the magnitude of this gap. Okay. So now you can try to see how much it will be on the earth because you know the radius of the earth. And so if you go for a kilometer and do this square, you will not be really, it will be very hard to measure this gap. Okay. Now comes the next thing, what is its direction? So it's a vector, so I have to tell you what is its direction. And here was a little surprise about the direction. I have drawn this picture correctly. See, in the case of positive curvature, the quadrilateral will overshoot. It will come like this, and it will come here. If P0 is here, then P4 will be here in the case of positive curvature. This picture is for negative curvature, where the geodesics are kind of diverging all the time. While for positive curvature, they come together and the point comes here. So here the vector, this violet vector that I have drawn, will come out to be like this. And then I can ask what is the angle between my starting vector u. That vector was red, so let me make it red here. This is the vector u, and there is this vector for the gap. This vector is this limit. And this angle is minus 45 degrees if the curvature is greater than 0. And plus 135 degrees if the Gaussian curvature is less than 0. So this is the answer to Rajaram Nityananda's question. Now, how does one answer a question like this? So like many questions in mathematics, you answer a question by first generalizing the question. So I'm going to generalize the question and then answer it, and then tell you how it is, how I could answer it. But I also want to give heuristic arguments which tell you how one can expect this answer, and where the mystery of 135 and minus 45 will also go away when the answer is properly stated. So let me state the answer first in a more technical form for the case of a surface with a Riemannian metric. And in that case, the answer is this limit s tends to 0 of P4s minus P0 upon s cube is equal to RUV applied to U plus V and the whole thing divided by 2. Okay, where this RUV is the Riemann curvature tensor. So now you have the manifold M, it has a metric, and this is the resulting connection. This is the Riemannian metric tensor. This is the Riemannian connection. So the answer is this, where RUV is equal to the operator nabla U nabla V minus nabla V nabla U minus nabla of the bracket U. So you take this operator and apply it to the vector U plus V and divide the answer by 2, and you will get this limit. So how does this immediately imply our answer, and where do these 45 degrees, 135 degrees, etc. come from? That is because in the case of a surface, this operator, this in a matrix form in an orthogonal basis, takes the form Gaussian curvature minus Gaussian curvature 0, 0. Okay. And now you apply it to your vector U, V. V is 90 degrees to U. And then you'll immediately get the answer. On applying this, you will get the answer U minus V by 2 times Gaussian curvature. And now U and V are unit vectors, so U minus V has length √2 and you divide by 2, that becomes 1 upon √2, and that's why the answer, the magnitude of the answer is the Gaussian curvature upon √2. Angle is also clear. U and V is an orthogonal basis, so U minus V is in 45 degree or 1 minus 135 degrees depending upon whether this is positive or negative. So the angle and its magnitude, everything becomes clear from this formula. So it is this formula that I'm going to prove. And this formula is my theorem in all dimensions. So M is any Riemannian manifold of any dimension, G Riemann metric tensor. This is the connection. And you do this exercise, but I have to then tell you how to perform this travel. Okay, so let's go to higher dimensions. So M is a manifold of dimension D arbitrary nabla is a connection on the tangent bundle of n. Okay, which means using nabla you can differentiate vector fields. This is the operator. With respect to a tangent vector, you can differentiate vector fields. It satisfies Leibniz rule. So I take it that you already know what is meant by connection on a manifold. Connection on the tangent bundle of a manifold. Okay. Once you have such a thing, there is something called torsion. This torsion tensor attaches to two tangent vectors at a particular point. So if u and v are tangent vectors to P, tangent vector M at point P, then this combination is well defined. In order to define it, you extend u and v arbitrarily to vector fields, and then so that you can form this bracket, you can do this differentiation, and then this combination is independent of how you prolong u and v from the point P to its surroundings, and it defines the so-called torsion tensor. And you also have the curvature tensor, which was defined as before, RQV, like this. Okay. So this is the amount of differential geometry I expect you to know, that what is meant by connection on a manifold, and the definition of torsion, and the definition of Riemann curvature. And so now I'm ready to state my more general theorem. The theorem is this. So in general, so let's call that statement number 1. In general, you will have limit s tends to 0 of P4s minus P0 upon s square, not cube, but square. This will be equal to minus, okay, but before even stating the theorem, I have to tell you the context. Okay, let's go down. Let's go down to the next. Okay, I'll have to insert a lot of space here. Okay, there we go. So now the quadrilateral, which Rajaram Nityananda suggested, has to be changed into the following. You start at any point P in the manifold and take any two vectors, u and v are any two vectors. There is no notion on a general manifold, there is no notion of unit vector, orthonormal vector, no such thing. So we just take any two vectors. Take them to be non-zero, otherwise the whole thing becomes trivially true. So take two non-zero, even linearly independent vectors. That's all that I ask you to take, two linearly independent vectors. And now when you go on a journey, so let's draw the journey in blue. You start from a point P and you go along the geodesic whose starting direction is u, whose starting vector is u, and you come to the point P1. So this point I'll call P0. And you follow the geodesic whose beginning tangent vector is u, and you arrive at a point P1. Now you parallel transport u and v, and you get two new vectors there. So when you have parallel, see the vector u is parallel transported all along the geodesic, because we are following the geodesic determined by the starting vector u. So we parallel transport it here and get a new vector u1. And now the second vector will, let's call it v1. As the second leg of the journey, you travel along the geodesics whose starting vector is v1, and you come to a new point, let's call it p2. Now you parallel transport u1 with it, and so you will get a parallel transport of u1. Take the opposite of that, call it u2, and now go along parameter s to a third point p3, and parallel transport this vector, this second vector, which you began with, u and v, parallel transport it here, parallel transport it there, and then travel along the minus of that, and you arrive at the fourth point P4. So this entire journey is made from these two vectors. First, follow the geodesic starting from P0 determined by u, carry u and v with you to that new point. Now follow the geodesic determined by v, meaning the parallel translate of v. Next, follow the geodesic determined by the parallel transport minus the parallel transport of u. And finally, follow the geodesic determined by minus the parallel transport of v, and end up at the point P4, which is a function of s. And so now one can ask what is P4s minus P0 upon s square, and this is equal to minus TUV, where this is the torsion. So in case there is torsion, the gap is of the order of s square, and the torsion can be recovered from this gap. And secondly, if the torsion is identically 0, then limit as s tends to 0 of P4s minus P0 upon s cube is equal to R u v u plus v upon 2. Okay, so I have finished stating my theorems, and so now rest of the time I'm going to make them look plausible to you, that yeah, one should expect such formulas. So here is a little linear algebraic calculation which MSc students should carry out by themselves, and that has to do with spaces which are symmetric. So one can think of, for example, sphere S2, and with metric so this is the Euclidean sphere. The metric on this is induced by the ambient metric on R3. This has constant curvature, so let's take this radius 1 or radius r. If I take x square plus y square plus z square equal to r square, then this has curvature k equal to 1 upon r square. So one can do this experiment. One can start with a point and move for s and carry out this whole quadrilateral that we started with, come back where we are and find out what is indeed the difference. This exercise can be done easily using linear algebra, because your starting data is a point P and two tangent vectors. You take them to be mutually orthogonal. So here's a sphere, here's the point P, and now there's a vector u, which means a vector u like this perpendicular to it, and another vector v perpendicular to both. So this P u v is an orthonormal basis. For R3. Take it to be positively oriented orthonormal basis. So now, given this basis, if I begin with the point P and travel along the geodesic, which is a great circle in the starting direction u, and then I am going to parallel transport this v all along the geodesic and get a new direction. Then I am going to travel along this new one, and then new one, and then new. So this PUV, or let's call it P0, U0, V0, here I come to a new point P1, and I am going to travel now in the direction V1, and I am going to carry with me the vector U1, which is minus of the parallel transport of U. So this P0, U0, V0 is going to become P1, U1, V1. This is a linear transformation. This is an This is an element of SO3 actually. It's a linear transformation. In SO3, because one orthonormal positively oriented basis is converted into a second one. And so to repeat this travel is to take powers of this linear transformation. So you can explicitly write down this linear transformation, which is a function of S. And now you can take AS to the power 4 and subtract the identity and take its first column. And that will tell you what is the quadrilateral gap. I won't do this linear algebraic exercise in front of you. It's there in my paper. And then immediately you get this answer straight away. This answer you read off from there because you know what is the Gaussian curvature for the sphere. This is 1 upon r square. This is minus 1 upon r square. A second experiment you can do is for constant negative curvature. So for that, what you can do is you can take R3, rather regard it as R2 plus 1, and on that you take the metric dx square plus dy square. Okay, let me put minus signs on this. Minus dx square. Okay. Let me take this negative. Minus dz square. This is the metric on R21. And inside this, take the surface S, defined as the hyperboloid, x square, z square minus x square minus y square equal to r square. This has two connected components. Take the one with z greater than 0. So this is how the picture looks. If I put this equal to 0, then that's a certain cone. And this is the hyperboloid of two sheets sitting in this cone. This is S. It is this cone is asymptotic to this hyperboloid of one sheet. Now the induced metric on S. So S gets a positive definite Riemannian metric of curvature minus 1 upon r square. So this is the analog of sphere. And now one can once again do this experiment on this. Once again, one begins with a tetrad, which is orthonormal with respect to the quadratic form, this one, rather than the positive definite one. And instead of SO3, the group is going to be the Lorentz group. SO2, 1 plus or 0, whatever, connected component of that. Once again, there's a linear operator A, which tells you how to replace starting point and the two starting vectors by a new point and two new vectors, and iterate it 4 times and subtract identity, etc., etc. And divide by s cube and take the limit, and you will get the answer that I have already mentioned. Okay. So if even before you do any, so this does not involve any differential geometry, because all that you have to know is geodesics on a sphere are great circles, and geodesics on this also are similarly described, easily described in linear algebraic terms. So you can do the entire exercise linear algebraically, and for the case of surfaces with constant curvature, the answer is very pleasant linear algebra. Now, when you want to do differential geometry, I'm going to make, actually I prove it without heuristic arguments, but for the sake of this lecture, let me make a heuristic argument. The heuristic argument is this. There are something called Riemann normal coordinates. And in terms of Riemann normal coordinates, any metric starts looking like a metric of constant curvature up to, so if I take a point P, there are coordinates x and y, where P is given by x equal to 0, y equal to 0. And then the metric ds square takes the form dx square plus dy square minus, I think, Gaussian curvature by 3. I may be wrong about such constants. And then there's a quadratic form which is the same in curvature 0 or whatever curvature, and mod m cube p star m, okay, where m is the maximal ideal in the local ring of infinity functions at the point p generated by x and y. And so this form, and I can write the coordinate form also for that. That looks like this thing in the bracket looks like y square dx square minus 2 xy dx dy plus x square dy square. Okay. Now, if I have any arbitrary metric, these terms are going to be the same. These terms are quadratic in x and y, and the cubic onward terms will differ. So if I have any other metric, and if I try to solve for geodesics, and I am only going to travel a distance s twice, because instead of traveling 4 times, I can as well simplify my calculations by looking at the alternative journey where I go here, here, and compare it with going here, here. Then one can see that the points P0, P2 and Q2, the points P2 for constant curvature, and let's call it P2 prime for variable curvature, are equal to each other mod s power 4. And similar things happen to the points Q2 and Q2 prime. This argument I am not going to make precise, but it tells you why one should expect this answer. So when I take the differences, P2 minus Q2 and P2 prime minus Q2 prime, up to the third order terms, they are the same. And so these limits after dividing by s cube turn out to be the same. This is heuristic argument number 1, that for constant positive curvature sphere, constant negative curvature hyperboloid, one can verify the formula by linear algebra, and then by using Riemann normal coordinates, it will follow for all surfaces. Okay, this is heuristic argument number 1. Now heuristic argument number 2, that is even more simple-minded, says that if I want to have the gap, so this gap P4S minus P0, I like to expand it as a series in U and V, some constant term plus some linear term. Suppose I want to expand it like this, then, and so these, so AIUV is a homogeneous polynomial of degree I in the variables U and V, meaning in the coordinates of U and V. So this clearly has to be 0, because when S is 0, we are back where we started. And our experimentation shows that there's really, our experimentation with surfaces shows that there's really no linear term involved. It's at least second order phenomenon. So this also has to be 0. Now, the simplest second order tensor you can make from the connection, and U and V is going to be the torsion tensor U and V. So you will expect this term to be TUV. In case that is 0, then you come to the next term. Now you know you have to make something from two vectors, and all you have is your Riemann curvature tensor. So I can't put u here, otherwise it will be 0. So I'll have to put v there, and I'll apply it to u. Problem is, if I interchange u and v, the gap changes sign, because I travel like this, and compare it with traveling this way. So this gap will change sign if I exchange u and v. However, this combination that I have written is not skew symmetric. So I need to skew symmetrize it. How do I skew symmetrize it? I'll interchange u and v and subtract this from it. So I am going to subtract r v u v and divide by 2. That is skew symmetrization. Do the transposition, subtract and divide by 2. To symmetrize, I add the transposition and divide by 2. So r v u is equal to minus r u v. So this term becomes plus r u v. So the entire answer becomes r u v applied to u, applied to v, and divided by 2. So u plus v upon 2. And so by purely symmetry grounds and grounds of magnitude with s, you will expect this term to be this. And indeed, it turns out to be so. So this heuristic argument is not a proof, but it tells you what to look for. Now about the actual proof. A few words about actual proof, because I do have a few minutes left. Dilip, how much time do I have?
Can take few minutes because we started a little late, no?
Okay. All right. Thank you. So I want to remind you that there is a very simple situation in which we consider gaps, and those gaps are for the flows of vector fields. So let me take two vector fields. This is a vector field. Now let me take another vector field. Okay. So to do your experiment, you can consider your red vector field. Try this. Take your red vector field to be, say, dy dx, and take your blue vector field to be x d by dy. Now a little experimentation shows that if I flow along the first vector field, then along the second vector field, then along the first, and then back, I don't get back, because you see, so let me draw this coordinates. This is the point 0, 0. So one vector field is the constant vector field d by dx, that is E1. And the second vector field is x times E2. So one is x times E2, which keeps on growing in size and is very tiny here, and one is E1. So if I do this journey, I flow along this, then I flow a lot, then I come back, and then I flow much less because the vector field has decreased. I don't get back where I started. And indeed, this is where, if I take the flow of the first vector field, if I start from a point P0, I flow along the first vector field for S, I flow along the second vector field again for S, P1, P2, then I flow along minus the first vector field for parameter value S. S is now the parameter value for your flow, which gives derivative U or V. And then you flow for parameter value again minus S. You come back to a new point, and this gap is, so you take the gap and P4S minus P0 and divide by S square and take the limit. This turns out to be the bracket of the two vector fields. Okay. So the Lie bracket . is really this limit. When I have the flow of two vector fields. So all this should remind one of something to do with flows of vector fields. Now, this analogy is what results into the proof of the first theorem. The first theorem proof I got out of the parallel between, because here also there is a denominator S square. This is a second order phenomenon. Torsion is a second order phenomenon. So that is a gap in the flow. And what flow? Where? Because actually you are only given U and V at one point. So you go to the so-called frame bundle, and on the frame bundle you can generate certain flows starting, and then take the bracket of those flows, and the bracket of those flows has to do with the quadrilateral gaps, and that gap's projection on the manifold is going to give you the quadrilateral graph of your original journey. So this I have said very rapidly, don't have more time left. And that is the proof of the first theorem. Now for the second one, this is the more interesting one. So I will just say what is the idea of the proof and stop. The idea of the proof is to very bravely expand everything in power series, and actually you can work with Artin local algebras over R. You can truncate everything. You can go modulo the fourth power of the maximal ideal and simplify your calculations, and bravely go ahead and solve differential equations which give geodesics over this Artin local ring. It's easy, relatively easy, a messy long calculation. To make the calculation easier, it is better to approach it by Q2S minus P2S and separately show that this equal to this. So when you do this massive Taylor series calculation, all kinds of combinations of the crystal symbols and whatnot come up. And then you notice that there is a big cancellation, leaving you with the Riemann curvature tensor formula in its crystal symbol form. And so this drops off basically by doing that calculation and cancelling various terms and grouping the remaining crystal symbols in terms of Riemann curvature tensor. You already know that you should expect the Riemann curvature tensor out of your heuristic argument. In the actual fact is I made the heuristic arguments after doing the dirty calculations and arriving at the answer. Okay. So now, finally, a little linear algebraic comment. The little linear algebraic comment is, if you know for various vectors U and V, okay, then you can recover the Riemann curvature tensor R, U, V, W by simple linear algebra. From here to here, you go by well-known symmetries of the Riemann curvature tensor. So quadrilateral gaps is all that one needs to have in order to one can define the Riemann curvature tensor in terms of quadrilateral gaps. This is what this shows. So this is all that I have to say, and I will end by once again wishing all the best to Professor Kulkarni. I'm sorry I'm not there actually, but I look forward to meeting him not too far away in future. And I thank the organizers for inviting me to give this talk. Thank you.
Thank you, Nitin, for the interesting talk. If anybody has a question, he can ask. I would also invite Professor Kulkarni to give his some comments. It will be better if he comes here.
Oh, Nitin, have you published this result?
Yes, already appeared last year. So
Where?
reference is in the abstract and also on archive. You can easily look either archive or MathSciNet, whichever.
See. Oh, so this gives a better understanding of the Riemann all this torsion and Riemann tensor.
Another
Right.
understanding, let us say.
Okay. Okay, I would look at I would look at it, yeah.
Thank you very much.
Any other questions? If not, I will thank the speaker once more for his interesting talk, and we will wait for the next lecture at 3 o'clock. Thank you, Nitin.
Thank you.
Hey, there is something in the chat. How do we react to that?
Yeah, it was given to him, but lecture started, so.
No speaker.
You have what? Abstraction about? Yeah.
देखो एक बार ये कैसे कनेक्ट है
Because this we can just put down, that's all. Sagar, should be put down. नीचे रखेंगे थोड़ा उधर से थोड़ा सा लिफ्ट करके हाँ नीचे रखते
Zoom is not recognizing your I think this.
in my
You
desktop
can quit Zoom once and then probably restart. Maybe then it will recognize because you connected later. Sometimes.
I'm trying to YouTube maybe
Actually, the person can sit here. Chairman, you can sit here. Okay, keep it on this. आपण शिफ्ट करू शकतो ना कुठे इकडे तिकडे शिफ्ट करू शकतो. We can. We have 5 minutes.
Mike very good yeah huh
After the position, the position side still down. It's not opening. Yeah. It's not opening. Yeah. Usually you are doing something. You can ask your question because you might be position side here. You can't very. It's opening. It's working.
is it working now I think
वो वॉल्यूम वो था वॉल्यूम वाला वो होता है वो वॉल्यूम
अभी आवाज 100% right. हाँ हाँ 100 है 100% कर दो 100%. 100 था. वहाँ लैपटॉप में 100 है यहाँ पे. दाऊदा को पोस्ट करो नहीं तो ब्लॉक हो जाएगा. अरे लीव मत करो भाई. लीव क्यों कर रहे हो? एक बार क्विट करके दोबारा आते हैं फिर देखते हैं. नहीं मत करो वेटिंग डोंट लीव. Make host someone then leave. Otherwise don't leave. There are 24 people now. Ask कोई दिया है वो वाला जाओ वो वाला. कौन है देखो. अगर मेरे मैडम कंप्यूटर ही उसी जगह देगा. There is already somebody else. Ask someone to speak. Just ask someone. Call someone. विकास यादव को बुलाओ उसको पता है तो बात करो. विकास are you there? राहुल को बुलाओ.
Hello. Yeah, I'm there.
Can you say something again? Then ask him to say something. Hi Vikas. Our audio is good and you are able to hear. Vikas.
Yes, we are able to hear properly.
And you people hear, no? So now it is working?
Yeah.
Huh?
See the screen.
Yes.
All right, I think it's a time to start our second lecture today in the first session. The next speaker is Professor Dani, who retired from TFR, and now he is in CBS DAE Center in Mumbai. He will talk on geodesics on the modular surface and continued fraction expansions of their endpoints. Over to Professor Dani. You unmute him now. It's okay.
Thank you, Professor Patil, for the introduction. Let me begin by expressing my best wishes to Ravi Kulkarni on the occasion of his 80th birthday, a rare occasion for many of us. And wishing him successful and fruitful future henceforth. Maybe we might call this the third inning. At 50, people call it the second inning, but now 80 is in the third inning. So all the best wishes, Ravi. So, and I thank the organizers for providing me this opportunity to say a few words on this occasion. I'm actually not very much in the area of geometry as such, but there have been things which have been related to geometry, and I've chosen such a topic for this occasion for the obvious reasons. And so let me begin by sharing my screen. Here it is. Yeah. The topic, as you see it on the screen, is geodesics on the modular surface and continued fraction expansions for of their endpoints. Now, I suppose the first part is something very familiar to, and in fact, perhaps something basic or elementary for the present audience. The second part also is kind of folklore and standard, but maybe not exactly from the perspective which I am going to need and provide to an extent. Okay, so let me move on to the next page. Yeah. Now, on the modular structure, I'll soon from the next page, I'll have some diagrams, but for the moment, to give the first introduction, let's just use the diagram-less formulation. So we're going to talk of geodesics, and actually it would be convenient just to look at one side of a geodesic, and like we prefer, it's always the forward side. Forward geodesics on the modular surface, and so each of them have a certain endpoint, which is on the boundary. That's a modular surface, and the hyperbolic plane has a boundary, and there is, for each geodesic essentially is represented by some geodesic in the hyperbolic plane, and hence it has an endpoint, and which is a real number. And the interesting part of the story is that there's quite an interesting interconnection between the geodesic behavior of the geodesic and the number theoretic, or specifically what one calls Diophantine properties of the real number, which stands for its endpoint. So, that's what it's about. And more specifically, the Diophantine properties that are involved are that we shall be concerned with are actually reflected in